Hello everyone. In this video we are going to learn what is Nernst equation, what is the description of Nernst equation, and what are different forms of this equation that we use commonly in chemistry, and based on this equation how different styles of calculations we commonly do under the heading of electrochemistry. Okay, let's start. First of all, you must know what is Nernst equation. It is an equation that is used to calculate exact change in standard electrode potential of a half cell or of a cell. So this equation gives us an idea whenever a change is made in the temperature of a cell, in the concentration of solution of a cell, how much change in the numerical value of electrode potential can take place. So first of all, what is Nernst equation? The Nernst equation that you can remember, it is E is equal to E naught plus RT divided by NF log natural of concentration of oxidized form divided by concentration of reduced form. This is a general form of Nernst equation that is commonly used in the electrochemistry. Now, what is the description of this equation? You must remember E. E stands for non-standard electrode potential. It is the numerical value of electrode potential that we calculate in the presence of non-standard conditions. For example, we may change the temperature, we may change the concentration of the solution for a given half cell, and what change will take place in the numerical value of the electrode potential, that will be known as non-standard electrode potential. E naught is the standard electrode potential that is always given in the question, and numerical value of E naught, they are available in the chemical literature. R R is another constant. It is commonly known as universal gas constant, and its numerical value is commonly available when we use this Nernst equation. The numerical value of R is 8.314 joule per Kelvin per mole. T is the absolute temperature, and this temperature must always be taken in units of Kelvin. Whenever we use Nernst equation, the temperature is always kept in Kelvin. N is another variable, and it represents number of mole of electrons in the oxidation or reduction of a half cell. Whenever reduction takes place, how many electrons are involved, or whenever oxidation takes place, how many electrons could be involved. That is equal to number of mole of electrons. F, again, F is another constant. It is known as Faraday's constant, and the numerical value of F that is commonly used, it is 96,500 coulomb per mole. This is the numerical value of F. Log natural, it is a mathematical method. The base of log natural is taken as E, and we normally use simple logarithmic form of Nernst equation. We will modify this log natural form into simple log form. uh, what is oxidized form? Whenever you have been given an element in two different oxidation state, the higher oxidation state, it is known as oxidized form, and the lower oxidation state, it is known as reduced form. For example, if you have been given a half cell containing Fe3 plus and Fe2 plus, Fe3 plus is the oxidized form and Fe2 plus is the reduced form. Also remember, whenever you have been given in any half cell a solid, liquid or a gas, the concentration of a solid, liquid or gas, it is always considered 1 mole per dm cube. So you can say that the concentration of a solid, liquid or gas, it is constant, that is 1 mole per dm cube. Okay, before calculation, let's modify this general equation, Nernst equation, into two different forms. One form, when you will convert log natural form into simple log form. But you must remember, log natural is equal to 2.303 log. So if you replace log natural in this general form of Nernst equation, what this equation could become? It could become E is equal to E naught plus 2.303 RT divided by NF log of, now log natural will be replaced by log of concentration of oxidized form divided by concentration of reduced form. So this form of Nernst equation, it is known as non-standard Nernst equation. Why this is non-standard form? This form of Nernst equation is used in numerical problems whenever we have been given temperature other than 25 degrees Celsius or 298 Kelvin. Whenever in a numerical problem temperature is other than 298 Kelvin, we will use this form of the Nernst equation. And whenever in a numerical problem the conditions of temperature are constant, that is we are available with 298 Kelvin or 25 degrees Celsius temperature, then we can use standard form of Nernst equation. What is the standard form? Whenever temperature is constant 298, then R is also constant, 2.303 is another constant, and F is also a constant. So what we can do with these constant, we just multiply and divide them and get another constant that is a constant for the standard form of the Nernst equation. Look at that. E is equal to E naught plus, if you just take the calculator, multiply 2.303 into 8.314 into 298 divided by 96,500, all the constant we have just used in this calculation. So what value you are getting? You are getting 0.059 divided by n, because n is a variable. Number of mole of electrons involved in an oxidation or reduction, they could be different, and then the remaining part of the Nernst equation, it will remain unchanged. Log of concentration of oxidized form divided by concentration of reduced form. This form of Nernst equation, it is known as standard form at a temperature of 298 Kelvin. Okay, now how and when to use which form of Nernst equation? Let's start doing some numerical problem. You will get to know how to use non-standard form or standard form. Let's look at this first question. In this question, it is the requirement to calculate the value of electrode potential at 273. You can see the temperature given in this question, it is non-standard. So for this non-standard temperature, you will use the non-standard form of the equation. So what you will do, you will insert the values. How you will insert the values? E is equal to E naught, standard electrode potential is given in the question. For nickel half cell, standard electrode potential is negative 0.25 volt plus 2.303 into 8.314 into non-standard temperature of 273 Kelvin divided by number of mole of electron. Now how many mole of electron will be there? Look at the half cell. In the half cell we are having nickel solid and nickel 2 plus ion. So what is the change in what is the number of unit of change in the oxidation state of nickel? 2. So what will be the number of mole of electron involved in this reaction? 2, and F is 96,500 coulomb. Log of concentration of oxidized form. Which oxidation state of nickel is higher? Nickel in the solid state, its oxidation state is 0. Nickel in the solution form, its oxidation state is 2 positive. So obviously 2 positive is the oxidized form. Its concentration is given 1.5 mole per dm cube, while nickel in its 0 oxidation state, it is a solid, so its concentration will be taken as 1. If you now just use these values and calculate by using the calculator, what answer you will get? That answer would be the non-standard electrode potential for nickel half cell, and it is negative 0.245 volt. So important thing is, you must remember, you must memorize the Nernst equation. Once you know the Nernst equation, the other numerical values will be given. You must take care to convert temperature always into Kelvin, and rest of the information will be available. You will have to insert the information appropriately, and then you can get the answer. Moving on, you can see some more question. For example, this question again, it is for nickel half cell, but now the temperature is kept standard, so you will have to use standard form of Nernst equation. What is the standard form? It is 0.0598 divided by n log of concentration of oxidized form divided by concentration of reduced form. Just insert the values, get the answer. Okay, if you have inserted the values, you can check it. So the answer that you would get, it would be negative 0.2448 volt. This is the new electrode potential, non-standard electrode potential of nickel half cell. Why again this is non-standard electrode potential? No doubt temperature is constant, but in this case we have changed the concentration of nickel solution. The concentration of the nickel's ionic solution, it is 1.5. The standard concentration is 1 mole per dm3. Okay, one more question you can attempt by using this, but in this case look at the question. The question is slightly different. In this question you have been asked to calculate the change in the value of electrode potential. Okay, you can use the standard form of the Nernst equation, since the temperature is 298 Kelvin, but the concentration of copper sulfate solution, it is non-standard 0.001. So if you insert the values, the answer that you can get, it must be change in electrode potential value. So how to get the change? You will ignore which part of the Nernst equation. You will not insert any value of E naught, because we do not need a new value of electrode potential. Rather, we want to see only the change. What change would take place in the half cell of copper? So which part of Nernst equation represent the change? After E naught, the remaining part represents the change. So you will start inserting value from 0.059 divided by 2, because there are 2 mole of electron, log of oxidized form copper 2 plus, its concentration is 0.001, divided by 1 copper solid. So the change in this half cell would be minus 0.0885 volt. So this is the change in the electrode potential of copper half cell if we change the concentration of copper sulfate solution. Moving on, based on Nernst equation, at different levels in chemistry, you can also be asked a question like this. So first of all, you may be given an electrochemical cell. You can see this electrochemical cell is made up of zinc and silver half cells. You can be asked to calculate the cell potential. What you will be available with? You will be available with the standard electrode potentials of these half cell. Standard electrode potential of zinc half cell is negative 0.76. And standard electrode potential of zinc half cell is positive 0.80 volt. Okay, this information will be available in the question. You are required to calculate standard cell potential for this electrochemical cell. Now how you will, there is a simple formula that you can remember. Standard cell potential, it is equal to standard reduction potential of cathode minus standard reduction potential of anode. But it is important how you will come to know which half cell will act as cathode and which half cell will act as anode. It is very simple. Simply look at the numerical value of standard electrode potential for each half cell, and whichsoever half cell is having mathematically greater value, that half cell would become cathode. It must undergo reduction. Then the cell will become electrochemical cell. And what is an electrochemical cell? Electrochemical cell is a cell that can produce voltage. So in this case, you can see which half cell is having the mathematically greater value of standard electrode potential. It is silver. So silver would become cathode. So you can insert the value reduction potential of silver half cell minus reduction potential of zinc half cell, because zinc half cell would act as anode. So the answer would be positive 1.56 volt. This much voltage will be produced by this electrochemical cell. Now this part of the question, it will be linked with Nernst equation. How? Look at the second part. You will be asked to calculate the new value of non-standard electrode potential for zinc half cell. Okay, use the non-standard, use the standard form, because temperature is standard, so you can use standard form of Nernst equation. Insert the values, get the new non-standard electrode potential for silver half cell. Now E naught standard cell potential is given, standard reduction potential of silver half cell is given. 0.059 is a constant. Number of mole will be 1, because silver is showing a change of 1 unit from 0 to 1 positive in its oxidation state. Log of concentration of oxidized form is 0.0002 and log of concentration of reduced form is silver solid, its concentration will be taken as 1. Just calculate it, you will get the new non-standard electrode potential for silver half cell, and it is positive 0.58 volt. So you can see the non-standard electrode potential of silver half cell, it has been reduced from positive 0.8 to positive 0.58 volt. Now, based on this change in the non-standard electrode potential, you will be asked to calculate the new cell potential. The formula of the cell potential will remain same, reduction potential of cathode minus reduction potential of anode. But as you can see, the reduction potential of cathode, it has been decreased. So that is why overall voltage of the cell electrochemical cell, it would also decrease. You can insert the value and you can see the change in the cell potential. The new cell potential would be positive 1.34. So this is lesser voltage compared to the voltage produced by zinc and silver half cell under standard conditions. I hope you would have enjoyed this video. Thank you for your time. Bye bye.